All right. There's the recording. Dr. Amidani, we're looking forward to your talk.
Thanks. So thank you. It's really a nice pleasure to be with you today and talk about some of the work we have been doing last years. So the outline of my talk, I will go through a brief introduction just to say a few words about actinides and the X-ray spectroscopy and calculation on actinides. And then I have a part one on a case regarding thorium dioxide nanoparticles, and a second part on the study of the local structure effects of uranium-6. So before going to the introduction, just a few words about me. So as it was said, I'm working at the Rossendorf beamline. So we are placed in Grenoble, so at the ESRF, the European synchrotron. The beamline has three main measurement stations, so we can do XANES, HERFD, and RIX, because we have an X-ray emission spectrometer, and we have two stations for XRD. This is the team, so as you see, and but we are operated by the Rossendorf Institute, which is in Dresden. So actually we are what is called a CRG, a German CRG. And we are dedicated to the study of actinides. The beamline is really thought to perform experiments on radioactive elements. And I joined the group in 2018 in the framework of the project led by Kristina Kvashnina and funded by the ERC. And my role in the group was to support data analysis with spectroscopy calculation. So my main work goes around the station with the X-ray emission spectrometer, and this is what I'm going to present you today. So why actinides are so fascinating? They are at the bottom of the periodic table, and they are characterized by the progressive filling of the 5F shell, which is determined their chemistry. So they are here, and they are in general poorly understood compared to other series in the periodic table. I saw that there has been other talks, very nice talks about the actinides in this SAS Journal Club. So it's just to repeat a bit myself maybe, but really actinides are, there is less that has been done compared to other elements. And maybe also because they have been last to be discovered, and they are often thought to be very similar to lanthanides. And indeed, this was also what I thought before joining Grenoble and having a look myself. And the lanthanides, which are characterized by the 4F shell, they have, so the 4F shell is well known to be very strongly localized and generally not participating strongly in bonds. So we can have a look to see if this is really the case for the actinides as well. And so here we are with the oxidation states of the lanthanides, so which is dominated by the 3+, as you see here, with few exceptions. If we go to the actinides, the table becomes much richer. And as you see, we have a full first half of the series where numerous stable oxidation state are found, while the second half is maybe more similar to actually what the lanthanides show. And what about if we look at the atomic radius extracted by the metals? So this is a line, this sort of almost line with a weak change with where we cross the series, is actually the radius of the rare earth metal. And this linear behavior actually is really typical of a series where actually the orbitals we are filling in is not participating to bonds, and so it doesn't change volume, which is totally different from what is observed for the transition metal, for example, the 5D, where across the series we have this typical parabolic shape. And if we look at the actinides, we see that the actinide metals has a double behavior. So basically in the first half, we see a sort of parabolic behavior to then go to a more linear behavior, which would mean that we have more itinerant 5F electrons involved in the chemical bonds in the first half, while we have localized 5F electrons in the second half. So the idea that they are really like lanthanides is wrong, and they have a rich chemistry, and they have a rich capabilities of localized or delocalized depending on the some factors, and therefore also to have 5F electrons which participate to bonds. So also the covalency of the 5F is something that is really interesting. And all of this complex, let's say, universe and rich chemistry can be investigated by X-ray spectroscopies. So mainly when we investigate actinides in the hard X-rays, because so we are at the synchrotron, which is optimized for the hard X-rays. We usually use L3 edge spectroscopy, where we excite an electron to the 6D states that are unoccupied, and eventually we can also look at the M4-5 edges, which are particularly interesting in this case because we go directly from a 3D 4 electrons to the 5F electronic shell. So those are the two main edges that we perform at our beamline when we investigate actinides. And we use an X-ray spectrometer. Why that? Because in the case of actinides, the increase in resolution that we can gain is really huge. So here I'm just plotting for you an example, what changes when we go for conventional or HERFD XANES at the L3 edge and at the M4 edge. So as you see, we really gain in we gain visibility of some structures that sometimes would be really hidden. And this is particularly true for the M4 edge. This is why M4 M edges in general are typically measured nowadays only with HERFD spectroscopy. And what do we want to learn? Of course, I mean, everything that SAS is sensitive to. So maybe the most known property is the sensitivity to the oxidation state, which is particularly pronounced for the M4, the M edges in general. Here I'm showing the M4 for the uranium 4, 5, and 6 plus. So the main absorption edge is really shifting, and it is measurable, and we can even quantify that. But also, I mean, XANES is very well known to be sensitive to the local structure and the projective density of states and covalency, and all these things are relevant in the study of actinide materials. What about then the calculations? Because so, as I told you, my role is to analyze data with calculations. The case of actinides is pretty well known not to be the easiest one. Indeed, we have a series of interactions which are very important. So we have spin orbit coupling, which cannot be neglected. At the same time, we can have important electron-electron interactions, and the crystal field, in the sense of the influence of the surrounding atoms on the absorber, is also maybe relevant. So we have to consider all these things, but it depends also which edges we are looking at. So if we stay in the L3 edge, the final state is delocalized, and so we can say that the electron-electron interaction are weak, and we stay in a certain framework. If we go to the M edges, of course, we are going to directly to the 5F shell. So we have a final state which is more localized, strong electron-electron interaction, not only between the 5F, but also with the core hole. So this means that we have a certain range of relevance of electronic correlation, which will change the approach we have to use for simulations. So in the case of L3 edge, the DFT approach is reasonable, because so in this approach, the electron-electron interactions are considered only partially. But this is, I would say, a safe case. What about the M edges? Probably we would immediately say, so we have to go to another framework, but that's not completely true. I mean, in fact, in some cases, specific cases, so for example, where we have 5F0, so because we have the empty 5F shell, or maybe with only one electron, still the DFT approach is reasonable. And why not to try what we get? But of course, as more as we fill the 5F shell, those interaction becomes important and the multiplet approach becomes more appropriate. So this is indeed what we do. So we use different codes depending on the case. Me personally, I use mostly XANES for the DFT approach, which is developed by Jolie, which is here in Grenoble. And at the moment, the code that we use when we go to the ligand field multiplet theory is Quanti, which is developed by Mark Maurits Avercourt in Heidelberg. So actually, this is the introduction that I wanted to give you. So briefly to summarize, I think that it's clear that actinides are not like lanthanides, and that the 5F can participate to bonds, and they are poorly known. That we can address with spectroscopy at the L3 and the M4-5 edges those elements, and that with HERFD we have indeed a huge gain. And in terms of calculations that are challenging, but still DFT can be quite useful, as I will show you. And we have the ligand field multiplet approach that is very well suited to treat stronger electron-electron interaction cases. So actually, I designed my talk to have a first question break here, if there are any. I don't know if it's too early. I don't hear.
I was drinking my tea. My microphone is off. Sorry. I have a question. So you had that wonderful chart. You don't have to go back to it, showing all of the different oxidation states that exist for the actinides, right. And in particular, that I think it was plutonium it just has everything. My yes. question is, if we wanted to see a compendium of HERFD or even a compendium of just the MEdge XANES for these elements, where would we find that resource?
I think that a single place is not yet available. And so I think that we have to surf around literature. Of course, I can suggest you to start from some of the papers that our group has published and go in references. But it's given not, for example, the 3+, I mean, these are stable, but not everything is easy to keep stable. So, for example, the 3+ is very rare, but we published something. And the 7+ I never saw.
Okay. We have a question. I've heard lanthanides are surrogates to actinides. Why should they be called that, given how different you're showing that they are?
Yeah, that's a good question. And so I'm not a chemist. I think that of course you can think how difficult it is to work with radioactive materials. So the surrogates are first of all very important to play around with in a safest way. And I think that, for example, in terms of ionic radius, they may be quite similar. At least one can find in the table of actinides some of them that can fit, at least for the property of the atomic radius. But then, as I said, I think that also how good they are as surrogates is a good question. I mean, I think we need more investigation for that. So.
All right, excellent. You should continue, please.
Okay, so I go back to. So, as I said, now going to some examples of how, like, the work with calculations can really help some scientific cases. I chose two things. The first part is on thorium dioxide nanoparticles, and the second on the M4 edge on uranium 6+. Now, I like to present those things as a completely two different problems. Like in the first part, XANES and my calculations are helping in a complex scientific problem. So you can imagine how many other techniques it would be useful to involve to understand this kind of topic. The other side is more, I like it a lot as well, it's more a fundamental understanding of spectra. So what I'm going to present is a sort of different kind of investigation. But I want just to underline that in the case of spectroscopy on actinide, especially when we go to high resolution, to my opinion, there is a lot also to do on this aspect of fundamental understanding of the spectroscopy. So I hope you will enjoy at least one of the two. But first of all, I mean, I start with acknowledgement just to not to be too in a rush at the end. So of course, the main acknowledgement goes to Kristina Kvashnina, which was leading this work that I'm going to present. And then these are the list of my collaborators for the case of the thorium nanoparticles. So in Moscow State University for the synthesis, and Gavin Vaughan here at ESRF for some measurements. And these are the collaborators for the case of the uranium 6+. So moving to the first example, so the thorium dioxide nanoparticles. Actually, I saw there has been a really nice talk from Liane Moreau on actinide dioxide nanoparticles, and already she introduced how complex this topic can be and how undeveloped the nanoscience in the actinide field is. So there are many questions that need to be answered. Are those nanoparticles amorphous or nanocrystalline? Which oxidation state they have? Which is the structure at the surface are among the questions. And I didn't note it here, but it's why they are relevant. As for sure, nowadays we know that they can be relevant for in the environmental contamination because they can travel a lot. And not only. So it's also a relevant problem for the technology or the environment. In this particular study, so our collaborators, Tatiana and Anna in particular, they were able to synthesize nanoparticles of thorium dioxide from chemical precipitation and get from a size of around 2.5 up to 35 by hydrothermal and thermal treatments. Of course, the first thing we look at is the XRD, and we notice immediately that when the nanoparticles are very small, the XRD pattern is not really well defined. And then it becomes more defined, and this is quite classic examples. Actually, it is quite debated what it is the first stages of nanoparticle synthesis. Are they amorphous? Are they nanocrystalline? And this is a nice review for the thorium dioxide case. And I would say that it depends a lot on which technique we are using to look at those samples. So if we go for XRD and EXAS, typically we would say more amorphous because of certain things. But for example, if we look at EM, we see some fringes. So actually we wanted to bring some contribution to this more structural understanding of nanoparticles. And our work started with the thorium L3H. So I joined the group, and those measurements were taken, and we see that at the L3H we have the sort of big nanoparticles like bulk that has this nice spectrum. As soon as we start to decrease the size, maybe already at 3.8, but especially at 2.5. We see that in the post-stage features that are 3 ABC, A is disappeared and C also is much lower. So actually this is a tiny effect. It's not a huge change in the spectrum, but we decided that we really wanted to investigate if this can tell us something. So of course we decided that we do it with calculations. And the first starting point for calculation is to have something that reproduces nicely the bulk, of course. So I'm using here FDM-NES, so I'm in the DFT approach, which is justified not only because it's the L3 edge, but also because thorium in the 4+ state, and generally thorium doesn't have F electrons. So I'm in an actinide which has the 5F shell empty. So I'm what I say, I'm on the safe side. So the simulation of the bulk actually it's pretty good. Very important is that we reproduce the post-stage structure that we are interested in. The white line is not at the correct position, but still the shape is good. But in these specific studies, I'm not focusing on the white line. because the scope of this investigation was to understand the effect of the surface intended as a pure absence of scatterers. So in this, I will not consider disorder at the surface or surfactants. And the nice thing of the white line, but also the difficult thing, is it is very sensitive, and we have to have, I would say, a structural description of our sample much more detailed to really trust what we see. So what I did, indeed, I cut it myself some chunk from a chunk of bulk thorium dioxide, some examples of nanoparticles of 2.2, 2.5 nanometers. And we went looking at the spectrum from single atoms inside. And here as an example, what we get is a simulation using, of course, all the same sort of framework that I showed you to simulate the bulk, but just changing the structural input. And if we stay in core atoms, so atoms that are inside the nanoparticles, as you see, they superimpose with the bulk. So the bulk spectrum is in black. And then as soon as we go to the facets, we start to see some tiny changes. And then we can go to the edge or to the corner, and we see that the changes are more pronounced. And especially that indeed the feature A that we are interested in is the one that is mostly affected. And we did, I mean, in this part of the investigation, I tried different shapes of nanoparticles, those three shapes that you see here. And it may be a bit messy, but these are sort of the atoms from those three shapes going from the bulk, the core, and then moving to the facets, subsurface, edge. And you see a sort of continuity on how we go from the structure of the bulk to, and little by little we lose the structures. And it's true that in particular, the A structure goes lower. And you can see that the only cases where we really don't have it is in the cases of corner atoms. So actually this first approach, this first investigation concluded, I mean, we were not able, by taking the full nanoparticle, to reproduce completely the spectrum if we average all the contribution from core atoms and surface atoms. But we could conclude that it was clear that the low A peak in the post-edge was clearly a sign of missing thorium atoms in the second shell. So here, just it's an extreme case where we go from a core to the corner. And this was our first conclusion. And we were happy because somehow we got some information that we can have. Then the investigation continued because we also recorded M4 edges on a similar set of samples or same preparation. And here you see this is the M4 of thorium. And we have the sample one that is the as prepared, the precipitate that we get just dried at 40 degrees. Then with mild annealing and strong annealing, we go from the blue to the dark red. So first of all, I want to underline how important it is to see that we see size effects when we are proving mostly 5F orbitals. This is already something that for us was really interesting. But actually, to get an insight in what was going on in this case, what really made the difference were other structural measurements. And this is also to underline the importance of using different techniques. On those nanoparticles, we measured also the PDF pair distribution function from high energy X-ray scattering. So here you see what we get. PDF basically is the probability to find atoms at certain distance. You see here the bulk. If I measure a bulk, I get peaks up to long range, more than 6 nanometers and over. Here I have 3.4 nanometers nanoparticles from XRD, estimated from XRD. And indeed, if I go around here, you see here that is 5 nanometers, I stop having oscillations. And those nominally 2.5, indeed at 0.5, I don't have any more oscillations. The nice thing is that PDF is easy to simulate if we have a structural model. And so we fitted and we actually got, so here I'm just for 1 second just showing you the fit that we obtained, which I consider very good fits. And so actually we were really able to get an insight of what is inside. So how we got those fits. Actually, the thing that I want to underline is especially for the sample number 1, which is the dried at 40 degrees. We initially, this is an approach that in PDF is done to estimate nanoparticle size. We just dump the signal with a sort of a function that takes into account the nanoparticle as a distribution of sizes. And this is what I was getting if I try to simulate the signal with basically this distribution of sizes. So I was getting quite, I mean, it's not a super bad fit. And I was getting a peak of size of nanoparticles at 0.5 nanometers, which is super small. But I was totally missing a lot of oscillation, as you see here. So if then I go and say, okay, let's do the fit starting from, I don't know, a bit less than 1 nanometers, I'm getting a very nice fit of the higher oscillations, and I get a peak at 1.5 nanometers. I totally get another distribution, but I miss completely the first peak. So this was a hint that gets us to the point of, okay, it's a bimodal distribution basically in this sample. But then another reflection came. So this would be the sort of distribution that I get for my 2 samples. What if I go now to see which kind of pieces of bulk I can cut? I mean, it's not a continuity of size that we can get. So because we are very small sizes. So basically, this is one of the smallest units I can get and is placed here. And so let's say it's what should be 0.5. The closest to 0.5 is this unit. Therefore, I decided actually that a more sound method to feed those data were to really trying to feed those more with ensembles of nanoparticles. And this is what we did through a program that is defined, which is dedicated to PDF. And this is where those nice fits come from. And what are they saying? The most important information that we got from here is that if we look what from diffraction, I was knowing being 2.5 nanometers nanoparticles. Indeed, we find that is a distribution and that the dominant contribution comes from something that is 0.56 nanometers, the smallest unit I can cut. And this is contributed 61% to my intensity. And this is the only way to include this kind of small pieces to get the first peak so high. And then we have a distribution of sizes. We did the same for the second sample, and we get this insight. What is really relevant is that this small piece of thorium dioxide that I cut is very similar to a thorium hexamer cluster. It is a cluster. It is a unit of 6 atoms that luckily chemists were already able to synthesize before, and so there are reports with the structures of those clusters obtained by synthetic chemistry. And this was really important to guide the analysis of the HERFD at the M4 edge. So here, so as I said, we have to start with a good fit, with good calculation of the bulk. So this is what I get for the M4 with the DFT approach with FDMS. Here we are so in a more delicate case for F system, but still. The density of states is in red and the spectrum is in black. So as you see, there is a sort of problem in the simulation because the second peak doesn't come out in the spectrum, but is present in the densities of states. And in the densities of states, I can so see 3 groups of peaks, 1, 2, and the small 3, which would be my A, B, and C. What if I take my small cluster that I use for PDF? I also get 3 peaks sharper, but still 3. And what if I go for the real clusters? Because those clusters have structures that have been published. And here, if I take the clusters that have been measured, I indeed miss the 3rd peak. That is what I see. This 3rd peak is peak C in my experimental data. And this is and why that? This is mainly because if I take the chunk of bulk that I cut it, I still have the octahedral symmetry locally. But in real clusters, the oxygen at the surface are rotated by 45 degrees, the symmetry is lost, and this is why the peak is lost as well. So this is to say that basically what we got from the information that we got from the PDF was fundamental to understand what we see in the M4 edge, and what we see in the M4 edge is compatible with the presence of those clusters. And then to go back to my L3 edge studies, so where my hypothesis was 2.5 nanometers nanoparticles, I think that simulations taking into account the presence of this small cluster would already bring us much closer to the result and to the disappearance of this feature A. Actually, I think that we could even get the result by just considering no relaxation of the surface, but just the presence of those clusters. Now, this is a tentatively. I would like to do a comparison of PDF and XANES, because XANES is a technique that is largely used to characterize those samples. So here is that, so I don't have XANES data, but I have, so here is what the PDF simulated by my unit, by my cluster cutted by the real bulk. And you see I have precise distances, so there is a coherence in the distances. This is the PDF of the simulated by the cluster. And you see, so in green, these small bars in green are the distances, and you see how they spread. And I want just to mention, and this is just to my opinion on that the fact that you see here the first peak, that is the thorium oxygen distance, is spreading over a series of distances, which is quite relevant to bring the coherence probably in the XANES signal, which has a much higher sensitivity, I think, to the at least of those measurements. And while you see that in my PDF signal, the first peak, despite the presence of different distances, is still not losing intensity. And then we still, and of course, the most important is that this technique has a sensitivity to the, not only to the short range, but also to the medium range. So we have a higher visibility. And so actually, in this example that I showed you as a summary, we have the small nanoparticles that in the L3 edge show a feature missing, and that we were able initially from calculations to ascribe this missing feature to the absence of thorium in the second coordination shell. And we had the hint that really we need to lower those number of seconds a lot to get this disappear. The PDF really got us towards a better characterization of this distribution of nanoparticles and highlighted the presence of those small clusters that were then necessary to explain indeed the data we saw at the M edge. And that the M edge really seems to be really sensitive for those clusters at the symmetry of the oxygen at the surface. And so this is everything for the first part. So I will take questions, if any.
Yes, there are a few. It's wonderful. Professor Pushkar, you have a question.
Hello, everyone. Nice to see everyone. So very nice presentation. So very quick, just clarification question. When you are talking about calculations of a L3H, and then you say surface atom or surface center or corner center, can you explain? Is like you compute entire cluster, or you just compute single center, and then how you terminate the coordination?
So yeah, so I'm simulating the single atom. So I can ask to the code I'm using to just give me the spectrum from a single atom. So depending on where this atom is sitting, then I was calling this a core atom, a surface atom, or a corner. And then I can compute the weighted average of all those atoms to get the final sort of spectrum for the nanoparticle that I didn't show. And regarding the termination, this is what was my, at the beginning of the L3 case, I specified it was a tentative evaluation of the surface as a bare missing of scatterers. So in fact, I'm not terminating the surface. And of course, this limits what I can say, for example, this is why I'm not analyzing the effects of the white line, which would be much more in the need to have a better description of the structure. So I don't know if it's clear, but why I'm not doing, because it is really hard to find realistic models of small nanoparticles of actinide. So up to now, I don't think that there are many theoreticians that can give me a structure of such a relaxed nanoparticle. So, and in the cluster is different, because in the cluster I have a real measure structure. This was key to simulate the M edges.
Okay, Dr. Haskell, you have a question.
Thank you. So you showed a pretty dramatic evolution of the white line as a function of nanoparticle size and shape, whereas the data shows a pretty insensitive white line. I was surprised to see that there doesn't seem to be a big influence of termination, surface termination effects or shape or anything. Can you clarify that, please?
Yeah, maybe I would say, maybe I would conclude the contrary in the sense, as I said, I mean, I was totally not considering the white line. I mean, in the end, I showed a big variation in the surface atoms, which somehow remains unmeasurable. I mean, I didn't measure the surface atom themselves, so I cannot say if the effect that I see in the white line resembles the reality, because if we then do the weighted average of everything, the dramatic effect that you saw would be like diluted in the core atoms. So I didn't show the average, but let's say it is not so dramatic. Still, there is an effect that is not completely the one that we see in the data. So to me, ideally, we should measure the L3 edge on a cluster to see what is really the effect. And I, as I said, to trust what I see in my calculation for the white line, I would like to have a more realistic structure of my nanoparticles, because I think that it is more sensitive, this part. So it is an open question. I mean, how big this is really the effect on the white line for surface atom, I would need to measure a cluster to really clarify. And this I don't have.
Thank you.
One last question. So ESRF after the upgrade has spectacular brilliance. And one of the main things that's affecting your analysis is that you may have a distribution of different nanoparticle moieties. Do you have enough brilliance, enough flux to disperse the nanoparticles, microfocus, nanofocus your beam, and look at the fluctuation in the XANES, particle to particle, nanoparticle to nanoparticle variation, and actually sample the distribution rather than modeling it?
Wow, that I think depends. I mean, there may be beam lines. I don't think that despite the spectacular brilliance we have, we still can go and have a beam that goes to 2 nanometers. So even the nano beams, I would say it's not my, I mean, I'm not working there, but
sure, but this is something to talk about, because you don't need to go to 2 nanometers to see a 2 nanometer particle, of course.
But
So
still
something to think about for the future.
Yeah, and then the point is how to disperse the thing that probably experimentally would be the most difficult is to prepare a sample where actually the nanoparticles are well dispersed, because they tend to clusterize. Like, so this would be maybe.
Then the second question is, what about eels?
Eels, to measure oxygen or?
Oh, I mean, they're doing eels to higher energy losses these days. I mean, pick your favorite edge, but it would let you, again, get spectroscopic information one moiety at a time.
Yeah, this would be really interesting, I think. And then there is the question of, I mean, the advantage of doing the measurements I showed is that the nanoparticles are staying in a more, in an environment which resembles more their real environment, because we can measure. This was a wet paste. So of course, when we go to vacuum, we still will have the question what vacuum is doing, but it doesn't mean that it's not worth to measure.
Okay. Excellent. I don't want to slow you down. You should continue, please.
Okay. So then I continue with the second part. I told you that this is more a fundamental understanding of spectroscopy. Why that? Because it is well known that MHs are has a so pronounced sensitivity to oxidation state. But what about the sensitivity to the local structure? So this is a question that somehow we had, and we wanted to address, and I think is not really addressed systematically in the community. So we had the chance to have M4 edge measured on a series of uranium-6+ compounds, and that we are showing the variability in local structure that was ideal for this study. So this is why I'm presenting you this. And why uranium-6 again? This is the electronic configuration of uranium, and if we go to the 6, then we lose all those electrons, and we again end up in an empty 5F shell. So again, a case where I can address where DFT has his own sense to be applied. And why DFT? What I like about DFT is that the way local structure, it's just automatic by the coordination of atoms that we get the information on how the local structure is. So somehow is a less approximated method rather than crystal field, to my opinion. And so let's go to the case. So we had those 6 solid samples that all contain uranium-6+, and where uranium has a local coordination that goes from 6 oxygen in a almost perfect octahedral configuration towards what is the prototypical case of uranium-6, which is uranyl, where we have 2 very short bonds with oxygen and then some equatorial ligands that can be 4, 5, or 6, but here we have 4. So basically we go to OH, D4H, and we have some intermediate cases. So this is, to look at how it evolves the bond lengths in between uranium and the ligands, the first coordination shell. So I said we go from almost perfect octahedra, which is called uranate, and then we go through 2 intermediate cases where you see we are lowering, and then the prototypical uranyl case with 2 short and 4 longer bonds. Actually, what group theory would tell us about just the splitting or the 5F shell that we expect in those cases? In the case of the uranate, we expect a splitting of the 7F orbitals will split in 3 groups. One just a single orbital pointing not towards the ligands, and then the TU group, this one, and the T1 group that is expected to be the more destabilized by the presence of the ligands, because indeed those F orbitals are pointing towards the oxygen. If we apply a compression and we go to D4H, we have a certain lift of some energy. So for example, we have, it's very easy to understand that the case of this orbital that is pointing towards the Z-axis is going to be more destabilized. And then we have those other groups. So what about the data? So first of all, just to verify that they are all 6+, we can put our M4 edges below the references, and we see that they nicely align towards the edge of the 6+. And having a closer look to our samples, we notice that basically we have the structure of the spectra are very similar. So we have a main absorption edge, and then a series of peaks so in the case of uranate and uranyl are 3 distinct peaks, so we can say A, B, and C. And in the intermediate cases, we cannot recognize the middle peaks specifically, but we clearly see the lower energy peak that is going from this energy to higher energies with the increase of the, let's say, bond distances, shortening of bond distances. And again, I said, so my approach was to use XANES, whose main input is the atomic coordinates of our structure. And then we, of course, we have some parameters to tune, let's say, the physics that we are taking into account. And then we can have as output the XANES spectrum, but also the projected density of states. And this is what we get as a best agreement, which I find pretty nice, because despite maybe each simulation is not perfect with the data, the trends that we observe in the series are reproduced. which I mean the presence or not of three features, especially the presence of this higher energy feature that is shifting towards higher energies. And let's say that the options, let's say, of FDMNS that we are key to get the results are specifically the considering the core hole and the spin orbit, relativistic effect as well, but mainly spin orbit. And when we have such a nice agreement in calculations like this, the insight into what we are observing is given by a detailed analysis of the densities of states. And this is resuming what we are expecting in the two extreme cases, in the case from group theory. And this is what are the densities of states when I'm simulating the uranate and uranyl without the core hole and without the spin orbit. And I can look at the specific orbitals, and indeed we can ascribe, in the case of the uranate, indeed the first peak is the A2U, is a single almost atomic orbital. Then we have a second group, T2U, and a third group, T1U, that gives this lower intensity. Similarly, in the case of the uranyl, we have three groups of orbitals that are contributing to the feature below the first main peak. And then we have the EU and A2U that are at higher energies. Adding the spin orbit and, in the end, the core hole is increasing the splitting of those main groups and bringing also the intensity closer to the experimental data. And so actually, after this insight from the density of states, if we go back to our data, we can say, first of all, of course, that our hypothesis was verified. I mean, the M4 edges at the uranium-6 clusters are very sensitive to the local structure. And what we can say is that in this series of elements, we found a sort of systematicity. The first peak A always is contributed by sort of non-bonding F orbitals, like that are less involved in bond. The high energy peak, this peak C, which in the case of the uranate is given by the three orbitals pointing towards the ligand, is then splitted by the compression. And it is here in this region that we expect the effects of covalency or any way to the change of the local environment. What is nice, I think, in this case, we also try to see what the crystal field, what approach would give us by using quantity. So in a crystal field approach, we have the degeneracy of the 5F, which is lifted by the field given by the ligands. And as I said already, in the case of OH, we expect this lifting, and in the case of D4H, this kind of ordering. The nice thing of quantity, I mean, if you are familiar with crystal field simulation, you are more familiar probably with the crystal field parameters called, I don't know, 10dq for the transition metals, or in the actinide, sometimes delta and theta. Anyway, the nice thing of quantity, or how we approached it, is that we didn't assign crystal field parameters, but we directly defined the energies of the orbitals that are determined by those parameters. And this we did because we wanted to tune the energy of a single group and see what was going on in the spectrum, to see basically it's really like twiggling here to see what in the spectra changes. And this sort of small game actually confirmed our interpretation based on the FT, because when we are in the uranate and we start to move the energy of this orbital, we get that the first peak is mostly shifting. When we go to the second group, I mean, there is a global shift. We didn't realign, but it's clear that the main effect is on the middle peak. And that in the case of the T1U, the third peak is the one that is affected. Similarly, if we go to the uranyl, the first three groups of orbital which we try to tune, we're all giving effects that can be sort of concentrated here below the first peak. And then the second EU group was affecting this peak that is below the peak B. And then, as you can guess, the A2U was moving here. So this was a nice confirmation from the crystal field approach of the interpretation of that we gave with DFT. And this is the best agreement that we can that I could get with the two approaches, which I said, looking at a single spectrum is not perfect, but here we are focusing on the trends. And I think this is also, it was giving a nice insight on what we can learn from the M4 edge on uranium-6. And with that, that was all I wanted to tell you. And therefore, this is my last break for question.
Do you have conclusions also, or is this the end?
No, this is the end.
Oh, okay, great. That's fine. No, that's great. It
Okay,
was wonderful. I just wanted to make sure. Okay, very, very good.
I hope that I convince you that calculations are very useful.
Yes, yes. We'll start with a question from Dr. Haskell.
Thank you. You know, in both examples, and I guess more relevant for the last one, you're showing M4 data and simulations, and you have shown effect or simulating the effect of spin-orbit coupling. And I was wondering, why not also look at M5 edges? And because that will give you quite a lot of information on the role of spin-orbit coupling, which I'm assuming to be important for uranium F3 or whatever this is.
Yes. Yeah, no, it's really true. And the simple answer is that I had mainly M4 data to calculate. But when we already saw that it would be nice to continue the systematic studies by going to M5 edges, indeed.
Because the branching ratios of the M4 and M5 edges are intimately connected to the spin-orbit coupling, right? So
yeah,
it should be quite dramatic changes between the two that should help nail down the models.
Yeah, I have to say that I tried also to simulate the M5, but in a certain way doing a calculation without having the data to estimate how good it is, knowing that a couple of parameters can really change. For me, it was a bit, yeah, it was a bit moving in the dark. So we would need really measurements, and we have the possibility to do those calculations indeed, and it would be very interesting indeed.
Thank you.
Okay, we have a question from Professor Chenglan.
Thank you, Lucia, for the nice talk. I have a question about the interpretation of the spectrum. So chemically, it is tempting to interpret the features within like several to 10 electron volt to non-bonding, anti-bonding orbitals involving 5F electrons. In your interpretation, it seems that the crystal field can capture most of the features. And also, what I'm wondering is that for thorium, since 5F is quite inactive, but you still have those several features within that range, does this mean that covalency is not necessary in this interpretation? And what is, yes, thank you.
Yeah, actually, I would not, I mean, the fact that crystal field is so, in this case, is explained to me doesn't exclude indeed covalency. The interpretation based on molecular orbitals, as you said, it has been published for uranyl, and indeed, basically the fact that this peak is moving is due to, I mean, the increased covalency. So maybe I want to say in the model of crystal field, I'm forcing the splitting of those orbitals by crystal field, but in a more accurate model, probably the splitting is coming by the formation of a bond. So to me, the two things are not opposite. And in the thorium case, we didn't do an analysis towards understanding the covalency, but I can say that the splitting that you saw also in the M4 edge is a sort of crystal field. So it's sort of anyway the influence of neighbors on 5F. But I think there is covalency there. So I don't see the fact that crystal field reproduces because I'm using a big crystal field parameters. But if I could include the covalency and probably get lower crystal field, but good agreement as well.
Thank you.
I'll ask the last question. So you're showing the XANES and you're showing the HERFD. Is there any information lost where RICS instead of XANES would tell you additional things that could constrain your model?
Yeah, I think so. As I said, I was playing a bit dirty. Like I'm showing systems where there are no F electrons in the 5F shell. So I would say that this for sure, it's going to, this is a case where we can assume that probably going from the RICs to the just a cut, we have less information that are lost. But I'm convinced that of course, we should move to simulation of RICs, and we have to take RICs planes and analyze them carefully. But I expect that the more the 5F shell is filled, the more rich would be the RICs, and the more we would lose by going maybe to the HERFD.
Okay, seeing no further questions, let's all thank Dr. Amidani for a terrific seminar.
Okay, thank you.
That was great. It was wonderful. And I'm going to stop the recording and people can unmute and